Thank you. Good morning, everyone. I hope you've enjoyed the two previous talks. Sure did. There's a lot of pressure presenting among such great speakers. So this presentation is about building isomorphic real-time React apps using another interpretation of Flux. So let's get started. First, let's step back about the purpose of React. It has a very neat API, virtual DOM and stuff, but at its core, the purpose of React is very simple. It enforces an invariant. This invariant is that at any point during the life of your application, the DOM should reflect a high-level description declared by you. This high-level description is a render function, which takes the current app state and returns a description composed of React elements of what the DOM should be. So when you write a React app, your work is narrowed down to essentially two jobs: declare components by extending the React.component class, and manage app state. And React does all the rest for you. I won't cover much how to write good React components, since it's actually the easier part to grasp, thanks to the goodness of the React API and its flourishing ecosystem. However, managing app state can prove challenging, so we'll discuss this part. Part of the app state is local and is stored in your component state. This part of the app state includes form inputs, checkboxes, etc. But there are parts of the app state which are not local, meaning they don't belong to a particular component. This non-local app state can be anything that isn't strictly tied to a single component and its descendants. Real-world examples include user preferences, navigation history, mouse position, user session data, etc. There are even more basic examples of non-local app state, when you need to share state between two components in different regions of the component hierarchy, as shown in the diagram on the right. For example, one could have a button in some region of the component tree, which affects a click counter in some other region of the tree. So the button component should be able to mutate the app state, and the counter component should be able to read from the app state. But as someone very clever once said, shared mutable state is the root of all evil. But since we actually need shared mutable state in real-world apps, because apps are stateful and there's nothing we can do about it, how can we manage app state so that everything doesn't blow up at scale? The traditional response to this question, which most of you know, is to delegate the management of app state outside of React components hierarchy into a pattern called Flux, illustrated by this diagram. The React component in green fire Flux actions in blue. Flux actions are handled by Flux dispatcher in orange, which in turn routes them to the Flux stores in purple. Flux stores are opaque data structures which can mutate themselves upon receiving actions. React components listen for Flux store updates and re-render whenever a store they are interested in is updated. This pattern is very useful because the data flow is unidirectional. It's easier to reason about and debug since you can keep track of the cause of each effect. But Flux gets actually useful when we add more components, as they can use Flux as a third-party single source of truth. Multiple components can read from the same Flux stores, but they cannot mutate them directly. However, they can send Flux actions, which will be routed appropriately to the Flux stores. Thanks to Flux, we can safely share app state between multiple components without exposing ourselves to the hazards of shared mutable state, since components have no way to mutate the stores directly. They can only fire actions, and when store receives these actions, they may or may not decide to update themselves, and in turn notify the components that they have. The components then may or may not decide to re-render themselves. Right now, I will show you that when presented very slightly differently, Flux is actually fully symmetrical. If we get rid of the dispatcher abstraction altogether, which is arguably an implementation detail, then the whole flow becomes fully symmetrical. React components receive store updates and send action intents. Flux stores, symmetrically, receive action intents and send store updates. It's very convenient to represent Flux like that because React component and Flux stores share symmetrical properties. For example, from the point of view of a React component, the store updates form the single source of truth. It can replay all the updates received since its instantiation and reconstruct its internal state from scratch. Symmetrically, from the point of view of a Flux store, the action intents form the single source of truth. It can replay all the actions received since its instantiation and reconstruct its internal state from scratch. Now let's see how this operates in an example. Let's say we wish to represent a button. Whenever you click this button, a counter is increased, and in turn, the label of this button is also increased. This is, of course, a contrived example, because in this case, you could achieve this using only component state, but let's see anyway how this works. So on the left, there is a simplified React component in a symmetrical Flux context. Here I'm using ES6 class syntax, but it will work pretty much identically using the legacy React.create class syntax. Also, I'm using a made-up Flux API for illustrating purposes, which contain methods such as this.getStore and this.getAction. Let's have a closer look at the code. In the constructor from the component, we subscribe to store updates from a store named clicks. Whenever the component receives an update from this store, we inject the new value into the component states. In the render function, we define a click handler on our button. Whenever the button is clicked, the component fires an action intent for the click action. So from the component point of view, the world is very simple. You can explicitly subscribe to store updates and fire action intents. And that's pretty much all you can do about app state. Now let's see the Flux store counterpart. Here I'm also representing a store with an API made up on purpose with a constructor and a render function to stress how symmetrical Flux store and React components are. This Flux store represents the amounts of times the clicks action has been fired. So it's a very dumb component. In the constructor of the Flux, it subscribes to the clicks action intent. Whenever this action is fired, the store updates its internal state by increasing its clicks state property. In the render function, we simply expose the internal state properties. Whenever the clicks value returned by render changes, a store update is fired, which in turn will be forwarded to each subscribing component. Here again, from the point of view of the Flux stores, the world is very simple. You can subscribe to action intents and emit updates by updating your internal state. So, let's step back again. Now we have React components and Flux store as symmetrical entities. React components receive store updates and fire action intents. They use an abstract onUpdate function to receive updates and an abstract dispatch function to fire action intents. Flux stores receive action intents and fire store updates. They use an abstract onUpdate function to receive action intents and an abstract update function to fire store updates. All you have to do is to implement these four methods as long as you enforce the two following semantics invariants. Whenever a Flux store calls update, then onUpdate callbacks will eventually be called by each subscribed React component, and whenever a React component calls dispatch, then onDispatch callbacks will eventually be called by each subscribed Flux store. One observation I would like to stress at this point is that how you enforce these semantics is totally up to the implementation. All you need is a communication channel. Using this communication channel, the update function can cause the onUpdate callback to be invoked, and the dispatch function can cause the onDispatch callbacks to be invoked. Therefore, as long as you have a communication channel, you can implement symmetrical Flux on top of it. And this really can be any communication channel. Okay. Note that we've established that any communication channel can support Flux. Let's explore a few of them that all you know. You have callbacks, promises, streams, event emitters, generators, coroutines, CSP channel. Basically, all the different idioms for timing the local event loop. That's usually how stock Flux and its multiple flavors are implemented. There's nothing new here, except maybe a nice little idiom agnostic symmetrical abstraction, but really nothing to be really excited about. You're probably familiar with this kind of Flux anyway. But it allows us to grasp that the communication support can really be abstracted away from the components and the stores. Now, things get actually more interesting if we use more exotic communication channels. Right, more interesting stuff. Post message with a web worker. This would allow us to defer expensive action resolution and store updates, such as sorting big chunks of data off-thread using Flux. That's cool, I think. And finally, WebSockets. WebSockets between a client-side JavaScript program running the React components and a server-side JavaScript program running the Flux stores. That looks promising, with a pun intended. Okay, so let's dive into this together. Flux over the wire, which is my fancy, cool marketing name for Flux using WebSockets, looks very much like stock Flux. Sorry. However, instead of carrying updates and action with event emitter or promises, we use WebSocket communications. On the left, you have a React component that live in JavaScript code running in a client browser. On the right, you have Flux stores that live in JavaScript code running in Node on the server. Updates are carried by server-to-client WebSocket frames. Actions are carried by client-to-server WebSocket frames. Things are very straightforward with a single React component. Now let's see what happens when we add more components again. Now let's imagine we have 3 React components. The first one lives in a client browser running React. Another one lives in another client browser, also running React. And a third one lives in another client, this time in a native iOS app running React Native. they can all connect to the same Flux server, implementing Flux over the wire, and share a single source of truth, which in turn they can affect by firing actions. Thanks to this pattern, we can now have shared state between multiple components, safely thanks to the unidirectional data flow of Flux, but they live on different clients. This would allow us to use Flux to implement multi-user React apps. The use cases are limitless, but let's examine the most obvious one, a multi-user chat. So on the left side, we have Visual running our React Native app on iOS. At this point on our server, the Flux store representing the shared state only contains one message, which is Pete saying hello. Visual writes a message on his app and touches the send button. The React component implementing this button fires a dispatch action function call. Under the hood, this action is JSON serialized and sent across the network through a client-to-server WebSocket frame. Upon receiving the WebSocket message, the server unserializes it, and the Flux store can then update its internal state. The store then contains a new message attributed to user Visual containing the text hello. Now let's see what happened on Pete's browser, which happened to be connected in a React app in its browser. At this point, the message list in Pete's browser only displays one message, which he had previously written. After updating itself, the Flux store calls its dispatch update method to signal that its public state has changed. The update is JSON serialized and sent to the subscribed client across the network using WebSockets. Upon receiving the WebSocket message, it is unserialized and passed to the message list React component in Pete's browser. Having received new props, the message list component re-renders and now returns an additional list item element. The DOM is then updated by React, and Pete can see the message retained by Visual on his screen. So now we can build chats using full-stack Flux. While showing a few slides to illustrate a thought experiment is cool, I've pushed it slightly a little further, as Vijay has mentioned. I'm very proud to introduce Nexus Flux, my implementation of Symmetrical Flux and Flux over the wire. All these libs are still in active development, so please feel free to file issues if they blow up in your face. And sorry for that. You can check them out right now on GitHub. The first lib, Nexus Flux, is a generic Symmetrical Flux implementation. Out of the box, it contains two simple adapters for local flux, aka stock flux, using event emitter, and a web worker adapter using post message. So the second lib, Nexus Flux socket.io, implements Flux over the wire using socket.io as its WebSocket abstraction / polyfill. The third lib, React Nexus, contains the React components decorators to hook Symmetrical Flux into your app. More on that in a few seconds. And finally, React Nexus Chat is a full-fledged demo app implementing a simple multi-user chat room using React Nexus and Nexus Flux. Okay, let's see how an actual React Nexus components looks like. Instead of mixins, here I use ES7 decorators that return higher order components. In this simple example, we implement a user component which subscribes to the profile of a user using a user ID and renders its first name and last name in a div. Once again, that's a pretty concrete example. Instead of having to know exactly your data dependencies beforehand at the router level, you can express data dependency directly at the component level, pretty much like in Relay. But in addition, the data dependencies can depend on props, so you can have dynamic data dependencies. Whenever the props changes, the data dependencies are diffed and resolved automatically using subscription batching. After the initial fetching, and every time the stores are updated, the up-to-date data store values are passed as instances of immutable js.map to allow instance reuse between updates and components. For the sake of this example, we immediately convert them into a plain props object and inject it downwards to the inner components props. So after the initial fetching, and every time the store are updated, the inner components get the new store's values passed as props. This means that whenever the data is updated, the component is re-rendered, unless you prevent it using should component update. You can react to updates in component will receive props, or simply read the current value declaratively from the props in the render function, like we do in this example. As I've just mentioned, React Nexus supports subscription batching. To illustrate what this represents, let's examine this example setup where three components subscribe to some remote stores. The first component, my component A, subscribes to two stores, /user/1 and /user/2. The second component, my component B, subscribes to a single store, /user/1. And the third component, my component C, subscribe to two stores, /user/2 and /user/3. So let's see what happens over the wire. A naive implementation of React Nexus would maintain one unique subscription over the wire per actual component's subscription. This would mean multiplexing exactly one update stream per subscription. But many subscriptions would be redundant. Both my component A and my component B depend on /user/1, and both my component A and my component C depend on /users/3. Bottom line, we would have to maintain 6 subscriptions over the wire when only 3 unique resources are depended on globally. But what's that bandwidth and CPU unnecessary cost? We would expose ourselves to inconsistency. The value for /user/1 in my component A could be different from its value in my component C. This would complicate our mental model a lot. But the implementation of React Nexus is slightly less dumb. The components don't communicate directly with the server. They delegate this to an intermediate object, the Nexus client. This Nexus client holds a deduplicated list of subscriptions required by the mounted components. Whenever a component is mounted or receives new props, the list of subscriptions is re-rendered, diffed with its previous version, and then the appropriate subscription and unsubscription messages are sent to the remote server. This batch subscription update happens at most once per turn of the event loop, pretty much like how React itself batches DOM updates at most once per turn of the event loop. As a matter of fact, this mechanism is actually tied to the React rendering cycle so that the subscriptions are updated at most once after each rendering pass. As a result, each active subscription is maintained exactly once over the wire. Whenever a remote store is updated, the Nexus client is notified by WebSockets, and in turn, forwards the new store value to the appropriate components. This has several upsides. First, we no longer have redundant traffic and calculation on our WebSocket channel. In this example, this allows us to reduce the number of subscriptions from 6 to 3. But again, more than that, we now have a consistent view of the value of each remote store in the whole component tree. So this example is just one of the many heuristics that React Nexus leverages to achieve production-level performance. I don't really have time to go over all of them, but there is some cool stuff under the hood. Fast object diffing with mutations, mutations recording, patch compression, clever use of HTTP cache with precise cache invalidation, etc. I'd be very glad to discuss them with you during the next break. One of the great features of React Nexus that I haven't even mentioned up until now is how it facilitates server-side rendering of isomorphic React apps that do data fetching. This problem is known to be relatively hard to deal with, as React is, at its core, a synchronous renderer. By streamlining data fetching under a common Flux abstraction, React Nexus is able to pull out the data dependencies recursively from your component tree, even the dynamic ones, fetch them all at once, and then render the component tree synchronously. In this example, we're using the Express framework alongside with React Nexus to perform server-side rendering. Nexus.renderToString replaces React.renderToString, but is asynchronous. React Nexus recursively fetches all the nested dependencies for you before synchronously rendering once all the data is fetched. It returns both the render HTML and the fetch data, so you can inject it into the response for immediate rendering on the client, avoiding this embarrassing moment when your app is made of spinning wheels waiting for your HTTP request to finish fetching data from your backend. Of course, at reconcile time, the data is still resynced with the server to avoid missing any updates, but it is completely transparent for the user. But wait, there's more. Of course, there is this demo app available right now at this address, react-nexus-chat.rotenberg.io. Please don't crash the server during the presentation, thanks. But it is also used in actual production website. To scale to tens of thousands of concurrent users, we rely on PostgreSQL, Redis, and Varnish to do the hard work, persistence, inter-process communication, and caching. We use this stack for the comments and user system of Millennium.org, one of the top French gaming websites. After successfully deploying our prototypes on Millennium.org, we're now building a full revamp of jeuxvideo.com, one of the biggest video games websites in Europe. Several modules, such as the comment system, will be deployed to other Webedia websites by the end of 2015. Okay, so it's time to wrap up. There are a few ideas I would like you to bring home. First, Nexus Flux is fully symmetrical. React components and Flux stores are dual, and they form a unidirectional data flow carried by updates and actions. Second, Nexus Flux can work over any communication channel. I haven't said much about cross-window Flux, WebRTC Flux, and WebWorker Flux, but there's great potential in that area too. In particular, Nexus Flux can work over the wire using WebSockets. Having both the React components and the stores living in the same place, like in stock Flux, is just a special case. In the general case, the client and the server, as well multiple clients, can live in different contexts, such as some client living in different browsers, and the server living in a node process on your data center. Last but not least, Nexus Flux, with the help of React Nexus, streamlines the expression of data dependencies at the component level and can greatly ease server-side rendering as well as batch fetching. Of course, there's still room for lots of improvements. Nexus Flux socket.io could use a custom binary protocol instead of parsing JSON. React Nexus could be able to render subtrees of components on the server to save round trips even after the initial rendering. The Nexus Flux API should be redone entirely and learn from the awesome Redux API, for example. I very much hope to discuss this with you guys, either here on Twitter or on GitHub, and to keep hearing awesome talks to get inspiration from. Final word, the React community is really awesome, and thank you very much for coming here, and thank you for listening. I think I've been speaking really, really too fast, so if you have any questions, I think we have some time left. Yes. Is there a microphone on the... Okay. Please ask very loud. I'm sorry, I can't hear you. Does it support REST out of the box? Actually, the Nexus Flux implementation of our socket.io is an extension of the REST paradigm. So basically, you implement your REST app, and it will just work with Nexus Flux socket.io. But you can, in addition, if you want to, provide the updates using WebSockets. So bottom line, yes, it does support REST, although you have to constrain yourself to a certain subset of the protocol. Yes? Yes, actually the Millennium comment system on the millennium.org website hooks itself to our legacy API, and there is a node service that proxies the request to the legacy API and to transform them into the Flux over the wire protocol. So you can check it out on millennium.org. And maybe I have time for one more question. Excuse me? I'm going to hear you, I'm sorry. Okay. we do it using custom link components, which basically add the cross-source the cross-source forgery protection directly into the links and the form elements themselves. So it's basically a component level issue. Okay, I think we're done. Thank you very much.